to start, and then you can probably either send in your questions through Slack or. So first, Rahul, congratulations again. Okay, on the best paper award. So I have a quick question. First, you said it's an online algorithm. So, but it looks like your algorithm, you need to solve that convex optimization program and then to get to the lambda star. So that means you do need to know kind of the lambda by the end of the, that sequence. Whatever sequence you're given, you need to know, at each node what's the input rate so that you know and how to solve the convex function. So that's my question. So, in what sense online, and then how do you estimate that lambda?
Right. So all we need is that the information about lambda is known ahead of time. How to split is given by the convex program solution. So the information available to begin with is that the rate of arrival at each source is known to you.
So so it's not really for any sequence. So you assume that the lambda is kind of given at each node.
Yes. So arrival rate. So the on average arrival rate is given to you. The exact sequence is not revealed to you ahead of time. That's only happening online.
Okay. So because like there is I would rather call it, because like in the general kind of open queue network setting, you can see that's a stochastic setting, but then it's kind of very different from computer science kind of terminology, because people, when you say online algorithm is for any sequence, then you derive the rate, right?
Right. So the second part, when we said worst case, that was exactly for an arbitrary input.
Okay.
And because of lack of time, we could not give details on that part. But similar results are what exactly is contained in the paper, which can be controlled by an adversary also.
I see. Okay. So any other questions? If nobody asks a question, I have actually a lot, because this happened to be I'm quite interested in the talk myself. Okay. So the other question I have is, you mentioned your decision is you're doing determining the speed and also the routing and the scheduling. So which part is the scheduling? Yeah.
So in this, in the stochastic setting, scheduling becomes kind of easy. It's just first come, first serve, or you're routing traffic according to as it comes along. So you're not really looking at job sizes as such, because all of them have exponential distribution.
Okay. So you're basically just doing first come, first serve.
Right. So in the stochastic setting, yes. In the stochastic setting, when worst case, their scheduling matters. But for deriving competitive ratio results, we had to assume that all sizes are equal. In which case, again, the scheduling actually goes out of the window. So eventually what it matters is routing and the speed you want to choose.
Okay. So yeah, I think from the talk, my impression is you're mostly doing just speed and routing, and the scheduling part wasn't clear. Yeah. Okay. Thank you. Okay. So one more thing is on the Theta network. Is that basically what's the physical meaning of in your competitive ratio upper bound? You introduced this notion of Theta network. What is the physical meaning of that? Yeah.
So that is just an expression, like way to express complicated expression we get for the competitive ratio that happens to depend on the length of the paths in the network. So as I said, if the network is well balanced in the sense that no two paths in the network for a particular source destination pair are different in terms of their lengths, then automatically you get that the theta network, which is just an expression, evaluates to be a constant. In case a source destination pair is kind of unbalanced, that there are very short paths and there are very long paths. In that case, by looking at it, you might assume that this competitive ratio becomes large, but there is a weighting going on weights going on with respect to the optimal solution of the convex optimization problem, which will automatically scale down the amount of traffic going through a longer path. So irrespective of how your network is defined, the competitive ratio, which is a product of two expressions, one which depends on alpha and other is theta network, is bound to be small. So theta network is just a elegant way of writing it, which needs to be evaluated.
So can we interpret that Theta network is the throughput of the network?
Not really. It's just a some sense how unbalanced the network is. That's what it's controlling.
Yeah, because it's quite related to my own work. I had a sequence of paper on throughput scalability and on full conjoined networks, and actually they're quite related because we look at exactly similar concepts. Like we look at scalability in throughput, like of C-balanced line networks, series parallel network, etc. So I just wonder what's the connection. Okay, thank you for that. So any other questions? Let me check Slack. Okay, good. So if not, we can move on to the next talk.